In the last video, we learned our most basic rules of differentiation, of taking derivatives. We learned the constant rule, which just tells us that the derivative of a constant equals zero. We learned the power rule, which shows us how to take derivatives of x to some power n. We learned our constant multiple rule, which tells us that when we have a constant in a function, we can pull the constant out and then take the derivative as usual. And then we learned how to take derivatives of functions with addition and subtraction inside of them. And we do that just by breaking apart the function by addition and subtraction. In this video, we're going to learn 3 new rules that will enable us to take more complex derivatives that we can't do with just these 4 rules here. We're going to learn the product rule first, and then the quotient rule, and then the third rule we're going to learn is the chain rule. To get started with the product rule, let's say that we have the function y equals x squared plus 1. You might immediately recognize that we don't need any new rules here to perform this derivative. We can take the derivative of this x squared using the power rule, and then we have addition, so we break the function by addition, and then we have the derivative of a constant, which is 0. So we know that the derivative of this function using our old rules is 2x. But what if we didn't just have x squared plus 1? What if we had x times x squared plus 1? We wouldn't be able to take this derivative directly with the rules that we have because we're dealing with a multiplication, and it's an x, so it's a variable. It's not a constant multiple. When we're looking at a function that doesn't look like it fits our rules for taking derivatives, our first thought should be, can we make it look like it fits our rules? And we can by distributing this x and multiplying. So we can rewrite this x times x squared, that is x cubed, because x to the 1 times x to the 2, our rules of exponents say that we're doing multiplication like this. We add exponents, so that's x to the 3. So we have x to the third, and then we have x times the plus 1, so that's plus x. And now, looking at this function, this distributed version, we can see that this does fit our rules. This is a power rule, and then this x is also a power rule. So we can do this in our head. The derivative, 3 comes down, subtract 1, plus the derivative of x is 1, because this is x to the 1. And then when we do a derivative, we bring a 1 down to be multiplied by it, and then we subtract by 1, which equals 0, and then any number to the 0 is 1. But what if we had a function like this? X minus 1 times x squared plus 1. Now again, this doesn't fit any of our previous rules, and we know that if it doesn't fit our rules, we should look and see if we can make it fit our rules. And in this case, we can also make it fit our rules. We can do the same distribution, we can FOIL this out, and we can simplify, and then take the derivative without any multiplication. But we don't need to do that. Instead of distributing and FOILing, we can take the derivative of functions that involve multiplication by introducing the product rule. So to set up the product rule and to take the derivative of this function without distributing or FOILing, we're going to write this term as f of x, and we're going to write this term as g of x. The same strategy that we used when breaking apart functions with addition and subtraction, except in this case it's multiplication. So our x minus 1 is going to be our f of x, and our x squared plus 1 is going to be our g of x. And I'm going to refer to those as the first and the second. You'll see why in a moment. So the product rule says that the derivative of f of x times g of x is equal to the derivative of f of x times g of x plus the derivative of g of x times f of x. The derivative of f of x times g of x, the derivative of a product, is equal to the derivative of f of x, the first, times g of x, the second term, plus the derivative of g of x, the second term, times f of x. The reason that I call these 1 and 2 is because it's easier to recite the product rule instead of thinking of it as f of x and g of x. You just think of it as the first and the second. So to say the product rule in another way, it's the derivative of the first times the second, not a derivative, just the second, plus the derivative of the second times the first. So on the left side, we're taking the derivative of the first and multiplying it by the second term. And then we're adding the derivative of the second term times the first one. So we can apply the product rule like so. The derivative of x minus 1 times x squared plus 1 is equal to, and here's where we follow the formula, the derivative of the first, that's x minus 1, times the second, x squared plus 1, and then we have plus the derivative of the second times the first, x minus 1. So now this was just setting up the product rule, following the formula, and now we just follow the ddx's and take the derivatives of these terms. You might think that this looks like a bunch of expanded mess, and that maybe it would have been better to just distribute and FOIL these two pieces out. And in some cases it is the easier method, but in some cases it's not. And by taking derivatives of these parts here, it's not the same as FOILing directly, because when we take the derivatives, these are going to simplify quite a bit. So we take the derivatives. So if we take the derivative over here, we have the derivative of x, which is just 1, minus 0. So we're going to have 1 times this bit here, x squared plus 1. And then we're going to have a plus. That's already this side done. So we're going to have plus the derivative of 2x plus 1. This plus 1 is going to be 0. So we just have the derivative of x squared, which is 2x. So we have 2x times this x minus 1. And now we're already a lot more simplified, but we can do more. We have x squared plus 1 plus, I just got rid of the parentheses here, plus 2x times x, it's going to be 2x squared, and then 2x times negative 1, it's going to be negative 2x, and then we can rewrite this a little bit. We have 1x squared plus 2x squared, that's 3x squared. Then we have negative 2x, and then we have a plus 1. So that is our answer using the product rule. Let's do another one. Let's say we have f of x equals 1 plus 2x squared times x minus x squared. Again, this would be possible to FOIL and distribute, but we can simply solve it by applying the product rule and not have to deal with all of that algebra. We have this term here, which is going to be our 1, and then this term, which is going to be our 2. So we have the derivative of this is equal to the derivative of our first. Again, looking back at our formula here, the derivative of our first, which is 1 plus 2x squared, times our second, x minus x squared plus, we have a plus here, the derivative of our second times our first. So now we set up the product rule by following the formula, and now we look at the ddx's and take the derivatives. So this is going to be 0 plus 4x, and then that's multiplied by x minus x squared. That's the left side done. Then we have plus the derivative of this. This is going to be 1 minus 2x. And just to keep things organized, this whole right side is being added. So I'm going to put a bracket here, just so that we don't get confused that we're adding this entire thing. So we have the derivative of this multiplied by this term here. So we want to indicate that by putting parentheses around it, because it's being multiplied by this whole piece here, the 1 plus 2x squared. And now our calculus is done, and we can simplify. We have 4x times x, that is 4x squared. And then we're going to have 4x times negative x squared. So that's going to be negative 4x cubed, because this is a 1 and then this is a 2 exponent. So that side's simplified. Then we have plus, and now we're going to have to FOIL this out. 1 times 1 is 1. Again, this whole thing is being added. So 1, and then we have 1 times 2x squared, so plus 2x squared. And then negative 2x times 1, so negative 2x. And then negative 2x times 2x squared, so negative 4, and we have x cubed. And now we can simplify one last time. We have 4x squared and then plus 2x squared, so that's 6x squared. Then we have negative 4x cubed, negative 4x cubed, so negative 8x cubed. Then we have a negative 2x, and then we have a plus 1. So that is our final answer. Let's do one that looks a little bit trickier. We have y equals the square root of x multiplied by x squared plus 1. Our first step here is going to be rewriting this square root as an exponent. And if you don't know, the square root of x is equal to x to the 1/2. So that's our first step. We have y equals x to the 1/2 times x squared plus 1. Now let's set this up for the product rule. We have the derivative of the first, x to the 1/2, times the second, x squared plus 1. Remember, we're calling this our first and this our second. So times the second, and then we have a plus the derivative of the second, x squared plus 1, times the first, x to the 1/2. So we set up the product rule. Now we take the derivatives. X to the 1/2. The exponent is going to come down, and then we're going to have x to the 1/2 minus 1. So that's 1/2 minus 2 over 2. That is negative 1/2. So x to the negative 1/2. And that's multiplied by this x squared plus 1. Then we have plus the derivative of x squared plus 1. That's just going to be 2x. I'm going to open a bracket here so that we know we're adding this whole piece to the other half. So 2x times x to the 1/2. Now, instead of distributing this 1 half x to the negative 1 half into this part here, we're going to rewrite x to the negative 1 half. We're going to rewrite that as, if you remember, when you have a negative exponent, you can move it to the denominator. So our x to the negative 1 half is going to become 1 over x to the 1 half. And remember, our x to the 1 half is equal to the square root of x. So we're going to write this as the square root, 1 over the square root of x. So when we rewrite this, we're going to have a 2 in the denominator with our square root of x. And now, writing it that way, we can put this x squared plus 1 on the numerator. So that's the left side simplified. And then we have plus, this is a lot simpler. We're just going to rewrite this x to the 1 half as the square root of x and get 2x square root of x. And that's our final answer. To take derivatives of functions like this, it's nice to introduce the quotient rule. And like the product rule, where we labeled the two parts that we're multiplying, f of x and g of x, we're going to label the numerator and the denominator. We're going to call the numerator f of x, and we're going to call the denominator g of x. But for the purposes of easily remembering the quotient rule, because it looks a little bit long, we're going to refer to the numerator as high, H-I-G-H, and we're going to refer to the denominator as low. You'll see why in a second. So the quotient rule says that the derivative of f of x over g of x is equal to g of x times the derivative of f of x minus, in the product rule we had a plus, but in the quotient rule we have a minus, minus f of x times the derivative of g of x. And that is all over g of x squared. And that's hard to remember, g of x times the derivative of f of x minus f of x and so on. But there's a little jingle that helps me remember the quotient rule using the word high for the numerator and the word low for the denominator. And that jingle is low d high, meaning the derivative of the high, the numerator. So low d high minus high d low, square the bottom, and away we go. So to remember our quotient rule, we just need to remember low d high minus high d low, square the bottom, and away we go. So we can take the derivative of this function by applying the quotient rule. And all we need to remember is low, our denominator, so low d high, the derivative of the numerator. By the way, the phrase low d high implies multiplication, the same as high d low. So we did low d high, and then we have a minus, then we have high, our numerator, multiplied by the derivative of our low, the denominator. And our last step, which is very easy to forget, and I have forgotten it on exams, is to divide by the low squared, by the denominator squared. So 3x plus x squared squared. Now setting up the quotient rule can be a bit tricky and a little bit annoying to get the terms in the right places. But after that, we follow the ddx's, we take the derivatives, and the derivatives are actually very simple. So if we take the derivatives here, we have 3x plus x squared times the derivative of 5x squared minus 2. This minus 2 is going to be 0. So we just have this 5x squared, constant rule, so we kind of So we know that we're going to multiply by this 5. So if we bring the 2 down, we're going to have 10x to the 1, or just 10x. And then that's this part already done. Then we have a minus sign, and then we have 5x squared minus 2 multiplied by the derivative of 3x plus x squared. So that's times, it's going to be 3 plus 2x. That is because the 3 comes out. This x to the 1 becomes x to the 0, which is 1. So 3 times 1 is 3. And then plus a simple product rule here. And then again, we don't want to forget, bring down the denominator. And we're not going to FOIL that out, but we are going to simplify the numerator. So at this point in the simplification, I had made a mistake. And ironically, that was because I did not use brackets around this part that we're subtracting, which meant that I did not distribute this minus sign when simplifying. So to simplify this, we have 3x times 10x, that's 30x squared, and then x squared plus 10x, that's plus 10x cubed. Then we have minus bracket 5x squared times 3, 15x squared, 5x squared times 2x plus 10x cubed. Negative 2 times 3 is negative 6. Negative 2 times 2x, it's negative 4x. And that is all over 3x plus x squared squared. We can distribute this minus sign and get 30x squared plus 10x cubed, and then minus 15x squared minus 10x cubed plus 6, and then plus 4x, all over our denominator. Now we can combine terms. The 10x cubed and negative 10x cubed cancel. 30x squared minus 15x squared is 15x squared. We have a plus 4x, and then a plus 6. And that is over 3x plus x squared squared. So that is our final answer. So the trickiest part of the quotient rule is probably just setting up our quotient rule, getting the low d high minus high d low square the bottom, getting that correct. Our third and final rule is the chain rule. The chain rule is probably one of the most important rules that we have for taking derivatives. If we have a function like f of x equals the square root of x squared plus 1, we would not be able to take the derivative of this with the rules that we have now. We definitely can't directly take the derivative of a square root. So we can rewrite this as x squared plus 1 to the 1/2. But that doesn't really help us get anywhere with our current rules. So we need a new rule for solving problems like this. And really what this problem is that it's a function inside of another function. This square root is one function, and we're going to say that it is y equals the square root of this inside bit. But for now, we're going to call it u. And I said that this is a function inside of another function. So this u is also a function. It is this inside bit. So we're going to say u equals x squared plus 1. This is a function inside of another function. So we just separated the square root and what's under the square root into two separate functions. And you can see we can piece it back together because we have the square root of u, and u equals x squared plus 1. So if we just put the u, x squared plus 1, back under the square root, we're right back where we started. So we just separated these two functions. So now the chain rule tells us that the derivative of y with respect to x is equal to dy du times du dx. dy du means the derivative of y with respect to u, and du dx means the derivative of u with respect to x. So what this looks like in practice is this. The derivative of x squared plus 1 to the 1/2. So if we just think of our inside function as u, what we want to do is take dy du. If we think of this as u to the 1/2, and we want to take a derivative of this, this is a simple power rule. We bring down the 1/2, and then we have u to the negative 1/2. We bring down the 1/2 and then subtract 1. So we get u to the negative 1/2 over 2. If we think of this as u, the inside function as u, and we want to do dy du, we bring down the exponent, the 1/2, and then we multiply it by u, and u is just equal to x squared plus 1. So we have x squared plus 1. And now we're still doing the power rule, so we want to subtract 1 from the exponent. So we get negative 1/2. That is this dy du. But we're not done. We still have the du dx. The du dx is the derivative of this inside bit that we've been calling u. It is du dx. It's the derivative with respect to x. And just to note, we have dy du and du dx right next to each other. So there's an implied multiplication there. So we did dy du, and then we have it multiplied by du dx, the derivative of just this inside bit. So the derivative of x squared is simply 2x, and then we have the derivative of plus 1 is just 0. So our calculus is done. We just did the chain rule. We did dy du by pretending that this inside bit is simply u, and then doing a power rule over it. And then we did our du dx, taking the derivative of this inside bit, and then multiplying it by the dy du. So if we simplify this, the 1/2 and the 2 are going to cancel, and we get x times x squared plus 1 to the negative 1/2. If we remember our exponent rules, we can bring down a negative exponent to the denominator, and we end up with x over x squared plus 1 to the 1/2, and our 1/2 is a square root. So we can write the square root of x squared plus 1. We have y equals the cube root of 5x squared plus x squared. If we want to take the derivative of this function, we need to rewrite this cube root as an exponent. And we can do that by writing y equals 5x squared plus x squared to the 1/3 power. Now we can see this is similar to our previous example, so we know that we're going to use the chain rule. And the chain rule tells us to take a derivative of our outside function, our u to the 1/3, and then take the derivative of our inside function, our d du, or the derivative of the inside. So again, if we just imagine our inside bit as u, or just know that we don't touch the inside bit, we can take a power rule over it. The 1/3 is going to come down, and then we're going to subtract 1, in this case 3 over 3, So our exponent is going to be negative 2/3. So we come back here. We didn't touch the inside bit, so that's still 5x squared plus x squared to the negative 2/3. That again is our dy du portion of the problem, of the chain rule. Next, we do our du dx, which is the derivative of our inside. So the derivative of 5x squared is going to be 10x, and then plus the derivative of x squared is 2x. Now if we do some simplification, we have a negative exponent here, and we have this 2 over the 3. So that is going to come down. Our 3 is down there, and then we're going to bring down our 5x squared plus x squared. And this is a cube root, but we have this 2 here. So it's going to be the cube root of 5x squared plus x squared squared. We can add this bit here, 10x plus 2x, that's 12x. And since it's being multiplied, we can bring it on top of the numerator and get 12x. So that is our final answer. Let's do one more example of the chain rule. We have y equals x squared minus 8 to the negative 7 plus 5x to the 4th. So looking at this function, our derivative contains addition, and we can see that we're going to be using the chain rule for this negative 7 exponent. The 5x to the 4th is a simple power rule with a constant multiple. So we would start with taking the derivative of our first term, the derivative of x squared minus 8 to the negative 7. Using our chain rule, we know that we take the derivative of the outside function and leave our inside function alone. So if we just think of this as u, our inside bit as u, we would bring down the negative 7 and then times our u, because it's the power rule, and then subtract 1 from our exponent to get negative 8. But that is only the dy du part. Now we need to take the derivative of the inside function, which is x squared minus 8. So it's multiplied by the derivative of the inside, which is just 2x. And now we completed the chain rule for this term. Then we have plus the derivative of 5x to the 4th. Pretty straightforward. Bring down the 4. It's going to be 20x cubed. We can simplify a little bit and bring this 2x to the front, multiply it by the negative 7, and get negative 14 times x squared minus 8 to the negative 8, and then plus 20x cubed. And I forgot the x here. That's negative 14x. There will be occasions, like in the following function, when we not only have a chain rule or a quotient rule or a product rule by themselves, but we have combinations of them. Looking at this function, we can see that we have an inside function raised to some power. So we know we're going to use the chain rule there. But then that's being multiplied by this 7x. So what we have is one term here being multiplied by this second term here. And this first term includes the power of 3. So when it comes to taking a derivative of this function, the first thing that we need to do is multiply, which means we need to use the product rule. And in the product rule, we take derivatives to both terms at some point, which means that during the course of the product rule, we're also going to be doing a chain rule. And I'll show you what that looks like. If you remember, the product rule is the derivative of the first times the second plus the derivative of the second times the first. So we set up our product rule, and like always with the product rule, once we set it up, we just take the ddx's. So when we go to take the derivative of this first part here, we can see that we have a chain rule. We set up our product rule, and now we have a chain rule. So to take the derivative of this piece, remember we ignore the middle. The middle is our u, and then we do a power rule over the u, over the middle. So we just bring down the 3, and then we have our u, our middle bit that we don't touch, we just bring it along. And then we're still doing the power rule, so we take our 3 and subtract 1 to get 2. Again, that's our dy du. Now we multiply by our du dx, so the derivative of our inside, which is just going to be 5x to the 4th, and then plus 0. So that whole part, this derivative, is multiplied by this 7x. Then we have a plus. So that's the first half. That's the left half of our problem. Then we take the derivative on the right side. The derivative of 7x is just going to be 7, and that's multiplied by x to the 5th plus 4 to the 3rd power. Now we can do a little bit of simplification here. We have a 3, and then we have a times 5x to the 4th. So we can write this as 15x to the 4th, still multiplied by x to the 5th plus 4 to the 2nd. And then this is still being multiplied by that 7x. So 7 times 15 is 105, I think. And then we have x to the 4th times x. So 105 to the 5th, and that simplifies that. Then we can't do any simplification here. We just have 7 times x to the 5th plus 4 to the 3rd. And that is our final answer. So to recap, the first new rule that we learned was the product rule. And the product rule showed us how to take derivatives of a function of x multiplied by another function of x. And the rule says the derivative of the first times the second plus the derivative of the second times the first. The second new rule that we learned was the quotient rule, which told us how to take derivatives of fractions, essentially. And if we refer to the numerator as the high, and we refer to the denominator as the low, we can remember the quotient rule with a little jingle. Low d high minus high d low, square the bottom, and away we go. D high meaning the derivative of high, the numerator, and d low meaning the derivative of the low, the denominator. And the third new rule that we learned is the chain rule. The chain rule showed us how to take a derivative of a function inside of another function, like this 9x plus 2 under the square root. The chain rule told us that we take the derivative of the outside function, the square root, while leaving the inside function alone, the 9x squared, taking a simple power rule of it, and then multiplying by the derivative of the inside, the 9x plus 2. So I hope you enjoyed this video, and I hope you learned something. There's still a lot of calculus to cover, so if you want to see more calculus, please like and subscribe, and I hope I see you in the next one.